discuss another concept, a very important concept called refraction of light. If you remember, we talked about refraction of sound waves in our last class. Well, 2 classes ago. What is refraction? Refraction occurs when a wave passes from one medium into another, and when that happens, there is a sudden change in speed, and the sudden change in speed causes the wave to change direction, and that is refraction. Now, if you allow a beam of light or a ray of light pass from air into glass, the sudden change in the medium causes a change in the speed of the medium. Now, the change in the speed of the medium causes a change in the direction of propagation of light, and that is what we call refraction of light. Now, in the same way as we defined in the case of reflection, let us define some terms here. This ray that is falling, now here I have a glass prism. Now let me see if I can show you one glass prism. Now here is a glass block. If I allow light, a ray of light, to go from air into this glass, its speed will suddenly change, its speed will decrease. As a result, its direction of propagation will change. That is what you see here, and we have the process called refraction. Now, this ray that falls on the glass is called the incident ray, and the ray that goes into the glass is called the refracted ray. So, we have the incident ray and the refracted ray. And what do you call this line? A line drawn at right angles at the point where the incident ray falls. This line is called the normal. And if you now measure the angle between the incident ray and the normal, it is called the incident angle or the angle of incidence. Similarly, if you measure the angle between the normal and the reflected ray, that will be called the angle of reflection. Now tell me, which of these angles is greater? When light passes from air into glass, the angle of reflection is less than the angle of incidence. On the other hand, if light goes from glass into air, I'm going to draw that for you there. If light now goes from glass, now this is light that goes from glass into air, it is going to go like this. So the angle of refraction will be then greater than the angle of incidence. I want you to understand this process. When light goes from air into glass, it bends towards the normal. You see this normal? It bends towards the normal. That means the angle of refraction is less than the angle of incidence. On the other hand, if a ray of light is going from glass into air, it is going to bend away from the normal because its speed is going to increase. And so the angle of refraction is greater than the angle of incidence. Okay? Alright. So as light passes from one transparent medium into another, air is a transparent medium, glass is a transparent medium, it changes its speed and therefore changes its direction of motion. We say it bends. When light enters from a less denser medium to a denser medium, now air is less denser than glass. Is that right? Yes. So when light enters from a less denser medium to a denser medium, that is from air into glass, it bends towards the normal. And that means the angle of refraction is less than the angle of incidence. Now this is because in a denser medium, the speed of light decreases. As light enters from air into glass, its speed suddenly decreases, so it bends towards the normal. Now, when light travels from a denser medium, if light now goes from glass into air, it is going from a denser medium to a less denser medium. Its speed is going to increase. It will bend away from the normal. Well, these two principles we will use as we go on. Now, this is why a stick in water appears bent. Have you seen when you put a stick in water, it appears bent? Why does it appear bent? Well, because a ray of light, suppose the stick is straight like this, a ray of light starting from there, when it reaches the interface, you see, it is going to bend away from the normal. Now it appears to be coming from somewhere higher. That means the stick will now appear bent. So the reason why the stick appears bent when it is put inside water is that a light coming from the stick, when it enters from water into air, it bends away from the normal. When you look from here, that light ray will appear to be coming from here. That means the end of the stick, instead of you see it there, you will see it slightly raised up. And that way you see the stick bent. The ability of a medium to bend light is called refractive index of that medium. The ability of a medium to bend light is called its refractive index. So every transparent medium has a refractive index. For convenience, we are going to take the refractive index of air as 1. That means the refractive index of water will be greater than 1. The refractive index of glass will be greater than 1. And look at the way we're going to define refractive index. We will represent the refractive index by the small letter n. And this is the definition of refractive index. Refractive index is speed of light in vacuum. That is where the light has the maximum speed. Speed of light in vacuum is the maximum value of the speed of light. So speed of light in vacuum divided by speed of light in a medium is called the refractive index of that medium. Alright, I want you to take note of that. The refractive index n of a medium is speed of light in vacuum, free space, divided by speed of light in that medium. Alright, let's do a small problem. The speed of light in quartz is 2 times 10 to the 8 meter per second. If speed of light in vacuum is 3 times 10 to the 8 meter per second, what is the refractive index of quartz? Well, all you need to do is write down that formula and put these values where they belong to. What's the formula? N refractive index of the medium is speed of light in vacuum divided by speed of light in that medium. Now, speed of light in vacuum is this, 3 times 10 to the 8 meter per second. And, well, that is this. Speed of light in the medium is quartz. Quartz is a kind of glass, and the speed of light in quartz is 2 times 10 to the 8. And you can see 10 to the power of 8 and 10 to the power of 8 will cancel. That will be 3 divided by 2, that is 1.5. The refractive index of quartz is 1.5. Well, let's do a small lab to measure the refractive index of glass. Now, let me see if I can actually show you what we are going to do. Mainly, I'm going to give you some values, and you will be doing some measurements of your own. And give me a second, I will tell you, I will describe the lab for you. Now, watch the experimental setup I have used here. I have allowed a ray of light, can you see that? A ray of light to fall on a block of glass. This is the glass block. Now, when the ray of light falls on the glass block, now this is quite misleading, because the ray that you see there is the ray that is going over the glass. You cannot see the ray going inside, but you look at this ray here. Can you see this ray? Well, that is the ray that is coming out. So what I'm going to do is I'm going to mark the positions of those two rays by means of 2 points. That's what I will do in the experiment. So let me show you what I'm going to do in the experiment. In the experiment, I will use an incident ray. I will draw that. And then I will draw this ray that is coming out of it. And then I can join the two. That will give me the position of the ray inside. Now, you can see if you watch carefully, when I change the angle of incidence, the ray that is coming out will also change. The angle of incidence changes will also change the angle of refraction. All right, now let me set up the some diagrams for you so that you can work on the lab. As I said to you earlier, we will trace the path of a ray of light entering from air into glass. This is the glass block that I used, and this is the light that enters the glass. What you call that ray of light? It is called the incident ray. And the ray that goes into the block is the refracted ray. Is that right? All right. So we have the incident ray, the refracted ray. That means we have, that is the angle of incidence. This is the angle of refraction. And what I would like you to do is draw a circle with its center at the point of incidence. Actually, on the worksheet, I have done it for you. I have drawn this circle. The circle is drawn with its center at the point of incidence. And now, let this circle cut the incident ray at A and the refracted ray at B. Is that right? The incident ray cuts the circle at the point A, and the refracted ray cuts the circle at the point B. Draw AC, that length AC, and draw BD. I think I have drawn those also in there. If I haven't, you must draw those lines. And then use your ruler. I'm sure you have a ruler that I have asked you to buy. Use your ruler to measure the length AC and the length BD. You can measure it in millimeters. Measure those distances both in millimeters, and then calculate the refractive index of the glass using this formula. The refractive index N equal to AC divided by BD. The length AC divided by the length BD will give you the refractive index of glass. Alright, so I have actually done 5 sets of experiment, and I have drawn these diagrams for you on the worksheet. You need to measure the length AC, the length BD, and write them down in the table. I have also provided the table for you. And then calculate the value of N for each measurement. Find the average of 5 measurements given in the worksheet and find the average value of the refractive index. And that is your lab. Alright, complete that lab. All these are very simple exercises. Alright, complete it then, email it to me. Let's now talk about critical angle. What is critical angle? In order to understand critical angle, you must understand the phenomenon I told you earlier. And that phenomenon is, this is glass. When light enters from air into glass, tell me, will it bend away from the normal or towards the normal? Well, when light enters from a less denser medium to a denser medium, it is going to bend towards the normal. Well, that means if a ray of light is entering from a denser medium to a less denser medium, it is going to bend away from the normal. Alright, understand this concept well. As light travels from a denser medium to a less denser medium, say air, the angle of refraction is greater than the angle of incidence. And now look at this. Here I have water and this is air. As a ray of light enters from water into air, what will happen? It will bend away from the normal. Let me draw that diagram for you. Alright, now I have a water down here and air up there. Now this is water. If I have a ray of light, this is a ray of light that is coming from water into air, and I draw the normal. It is going to bend away from the normal. Now, a ray of light that is coming from water into air, it is going to bend away from the normal. You see, as light travels from a denser medium, water is denser than air. A denser medium like water to a less denser medium like air, the angle of refraction is, this is the angle of refraction here, the angle of refraction is greater than the angle of incidence. That means if you keep on increasing the angle of incidence, the angle of refraction will also increase. A time will come for a particular angle of incidence, the angle of refraction will be exactly 90 degrees. That means the light that is emerging will go parallel to the interface. Now, this angle of incidence in the denser medium, which produces an angle of refraction of 90 degrees, is called critical angle. Alright? I will repeat that one more time. Now, for a particular angle of incidence, theta I, you see, if this is theta I, for a particular angle of incidence, theta I, theta R will be 90 degrees. And this value of the angle of incidence, well, that is your theta I. Let me write that for you. That is, so for a particular angle of incidence, theta I, the angle of refraction will be exactly 90 degrees. And that particular angle of incidence is called the critical angle. Now, can you tell me, if now the angle of incidence is greater than the critical angle, what will happen to the ray? You see, earlier you had the angle of incidence less than the critical angle, the ray emerged into air. Now, for the angle of incidence equal to the critical angle at this time, then the ray goes parallel to the interface. If I now increase the angle of incidence, what would you expect? The ray will come back to the denser medium. All right. Let me remove that now. There you are. This angle of incidence we call the critical angle, and I have represented by theta c. So if I ask you to define critical angle, what will you say? Critical angle is the angle of incidence in a denser medium which produces an angle of refraction of 90 degrees in the less denser medium. Now, if the angle of incidence is greater than the critical angle, if now the ray falls from water to air at an angle greater than the critical angle, the ray will simply be reflected back. So here I have the angle of incidence greater than the critical angle, and the ray does not go into air anymore. It is reflected back into water. Now, this phenomenon is called total internal reflection. In other words, the ray is totally reflected back into the medium. Now, I have shown an illustration here. This is water, and of course that is air. I have light coming from water going into air, and I have adjusted the angle of incidence such that the angle of incidence is greater than the critical angle. Now look at the angle of incidence there. Now this is the normal, and this is the angle of incidence. That angle of incidence is greater than the critical angle. So the ray of light is now incident at an angle greater than the critical angle. The ray simply gets reflected. Now this is total internal reflection. Now let's now talk about refraction in a triangular prism. If you allow light to pass through a triangular prism, what will be the path taken by a ray of light? Now here I have a triangular prism. Can you see the triangular prism? Well, let's see if I keep it close to my face. There you have a triangular prism. The prism has a base. Now this is the base, and these two are refracting surfaces. So my question is, my question is, if I allow a ray of light to go into one face of the prism, how will it be emerging on the other face? Alright, I'm going to try and show it to you. I have a ray of light here, right? I'm going to allow that ray of light to fall on one face of the prism and see how it is going to emerge. Alright, let me cut off the lights and see if it makes any difference. Alright, here is the prism, and see if you can see the emergent light. Well, can you see what happens? Now look at the ray that falls on the prism, and look at the light that comes out of it. You see, in the absence of this prism, the light would have gone, can you see where I'm drawing with my finger? It would have gone like this without any change. Now, because of the prism, it bends so much, it has gone all the way down here. So, what makes it go like this? What makes a ray of light that enters the prism like that bend like this? All right, let's take a look at that. Okay. Now here I have drawn a glass prism here. Now that's the base. This is one face. That is the other face. And when light passes, now I have told you how important that particular statement I have been making. Now look at this again. When light passes from air into glass, it is going from a less denser medium to a denser medium. It will bend towards the normal. So when light passes from air into a triangular prism, first it goes from air into glass, bending towards the normal. Then it has to go from glass into air, bending away from the normal. So when light enters from air into glass, it bends towards the normal. Watch that. Now here's a ray of light. This is the normal. This is now going to bend towards the normal. There you are. You see that? So that the angle of refraction is less than the angle of incidence. So a ray going from air into glass is bending towards the normal. Now what will this do when it goes from glass into air? It will bend away from the normal. Now look at, this is exactly what we saw in my demonstration. A ray of light entering glass like this comes out in that direction. In the absence of the prism, the ray would have gone that way, straight. But because of the prism, it actually bends twice. Once when it enters from air into glass, and the second time when it enters from glass into air. It bends twice, and as a result you can see it bends towards the base. Is that right? If the ray goes in like that, the emergent ray is now coming towards the base. There you are. This causes the emergent ray to bend towards the base of the prism. Alright, think of another prism kept inverted and the ray enters it as shown. Well, I got another prism, and if I have a ray entering that prism like this, can you trace out the path of that ray? How will that look like? You can see this ray will bend towards the normal, and it will go like this. It will bend towards the normal, and when it comes out of the glass, it will bend away from the normal. Is that right? There you are. Again, the emergent ray is bending towards the base. So, as a result, if you have a beam of light coming and entering two prisms kept like this, the emerging rays will converge to one point. Is that right? These two rays are actually converging to one point. There you are. Now, two light rays entering the two prism system converges on the other side. So these two light rays are actually converging to each other. And this is what happens when a beam of light passes through a two prism system. Now this is the principle of working of a lens. Have you seen a lens? Well, if you wear glasses, you are actually wearing a lens. Alright, let's now talk about lenses. Well, now you know what actually a lens is. A lens can be made by putting two prisms together. Is that right? If you have two prisms, put them both one base down and the other base up. That combination will be a lens. Here I have a combination of two prisms. You see that there are two prisms. If I place the two prisms base to each other, this is actually a lens. If I allow two light rays to go in here, when they emerge from here, they will both converge to a point. And this is the principle of a lens. A lens is a collection of prisms. Now look at this. A collection of prisms so that the bases are all facing together. And if a parallel beam of light entering that collection of prisms will all converge to one point. On the other hand, if you place the prisms the other way around, now what happens if you place the prism like this? Do you see what I'm actually doing? It's difficult for me to... Now, if the prisms are placed with the pointed end touching, what will happen? A beam of light entering will diverge. It will produce the opposite effect. So, when prisms are all kept the bases facing each other, if a beam of light is converging on the other side, if you place the prisms the other way around, a beam of light coming from one side will all diverge on the other side. That means if you look from this side, these rays will all appear to be coming from a point on that side. Now, depending on the shape of the lens, a lens could either produce a converging effect or a diverging effect. So you can see a lens like this is called a converging lens, whereas a lens like this will be a diverging lens. Tell me, what is the physical properties of a converging lens? A converging lens will be thick at the center, and as you go to the edges, it will become thinner. That is a converging lens. Thick at the center and thin at the edges. Whereas a diverging lens will be thin at the center, and as you go towards the edges, they will get thicker. Is that right? That is a diverging lens. Now here I have a diverging lens. Well, can you see this? Its center is thin. As you go to the edges, it gets thicker. And here I have a converging lens, which is thicker at the center and thin at the edges. Now let's see what happens when I allow a beam of light to pass through. Let's see if taking away the light will help. Alright, now try and watch this. I'm going to... Alright, now what happens when the beam of light is passing through this lens? It is converging. Have you seen the convergence? There is the beam of light. When it passes through the converging lens, it is actually converging to a point where I'm touching now. Once again, that's the beam of light, and when it passes through the converging lens, it produces convergence. Now, what happens when the beam of light passes through a diverging lens? See what happens. It produces divergence. So, a converging lens and a diverging lens. Now, you must be familiar with both these types of lenses. We will now see how images are produced by a converging lens. You can see this is the converging lens. And for that, we're going to make some definitions. Now, this is the converging lens, a horizontal line that passes through the center of the lens is called the principal axis of the lens. Now, for a converging lens, a set of parallel rays, if you now allow a set of parallel rays to fall on the lens, see, I allowed one ray to fall on the lens, look at the way it is going to emerge. It is going to be converging to one point. Now, another ray entering the lens, look at the way it's going to go. A third ray entering, it's going to go that way. A fourth ray, it's going to go that way. So what can you say about a set of parallel rays falling on the lens after refraction, after passing through the lens, will all converge to one point on the principal axis. And that point is called the principal focus of the lens. So a lens has a principal focus. I want you to know the definition of the principal focus. A set of parallel rays parallel to the principal axis after passing through the lens will all converge at a point on the other side of the lens. And that point where they converge is called the principal focus of the lens. We will represent that by the uppercase F. There is a principal focus F on either side of the lens. If the set of parallel rays are now coming from the left side, they will all converge on the right side. So there is a principal focus on the right side of the lens. There is one on the left side of the lens. The distance from the center of the lens to the principal focus is called the focal length of the lens. We will represent the focal length by the lowercase f. So the focal length is the distance measured from the principal focus to the center of the lens. You can see the illustration I just showed you. A parallel beam of light after passing through a converging lens will all converge at this point. What you call that point is called the principal focus, represented by the uppercase F, and the distance from the center of lens to the principal focus is called the focal length. You see, we will represent that by the lowercase f. The uppercase F is the point called the principal focus. The lowercase f is the length, the distance from the center of the lens to the principal focus, and we call it the focal length. Now, for a diverging lens, what happens to a diverging lens? For a diverging lens, a set of parallel rays falling on the lens after passing through the lens will all diverge. Alright? For a diverging lens, a set of parallel rays that are parallel to the principal axis after refraction appears to diverge from a point on the same side of the lens. This is the principal axis. A set of parallel rays that is falling on the lens. After passing through the lens, they will all appear to be coming from that point. So if you look from here, these rays will appear to be coming from there. Alright? And that is the principal focus of a diverging lens. And the distance from the principal focus to the center of the lens is the focal length. Now, we will now look at images formed by a convex lens. Images formed by a convex lens. We will now look at images formed by a convex lens. A convex lens is a converging lens. Now, the size and position of the image formed by a convex lens depends on the position of the object. Now, for example, I have a convex lens here. This is a convex lens. It is thick at the center and thin as we go to the edges. Now, I have an object here. I'm going to light up a bulb. Now, this is an object. Well, you can see that object. I can actually form an image of that object on the screen. Well, I have to black out the light. Now, if you look, I can actually form an image of this. I'm going to lower the bulb so that I can show you the image on the screen. Now, watch the image of the filament. Now, you saw the image, the same image on the pinhole camera the other day. Is that right? Now, when I move the lens, you can see the image, its size and its brightness, everything changes. So, the nature of the image is going to depend on where the object is placed. The size and position of the image by a lens depends on the position of the object. Now, we are going to use three distinct ways to construct images. I want you to watch here. So this is the convex lens, and review some of the terms that we used about a convex lens. A convex lens has a principal focus. Now, what is the definition of the principal focus? A ray of light parallel to the principal axis, after passing through the lens, will pass through a point on the principal axis on the other side. That is the principal focus. Alright, now I have marked the principal focus. There are two principal foci, one on each side, and this is called a 2f. Now, if this distance is one focal length, you know what a focal length is? Focal length is the distance of the principal focus from the center of the lens. So if this is one focal length, the distance from the center of the lens to the 2f will be 2 times the focal length. The 2f for a lens is like the center of curvature for a mirror. A ray that passes through the center of the lens will not suffer any deviation. It will go without deviation. And a ray passing through the principal focus after passing through the lens will go parallel. Now, these are the three distinct rays we are going to use to construct images in a convex lens. What are those one more time? A ray, a light ray that is parallel to the principal axis, after passing through the lens, will go through the principal focus. A ray that passes through the center of the lens will not suffer any deviation. It will go straight on. A ray that passes through the principal focus, after passing through the lens, will go parallel to the principal axis. And where is the image formed? The image is formed where light rays actually converge. In other words, after passing through the lens, these refracted rays, you understand what refracted rays are? Rays that after passing through the lens are called refracted rays. They will meet at a point, and the point where they meet is where the image is obtained. Now, when the object distance is more than twice the focal length, now here I have kept the object more than twice the focal length. Where is the image formed? you can see the image is formed between f and 2f on the other side of the lens. Now what can you say about this image? Is this image bigger or smaller than the object? Obviously the image is smaller. Now the object is erect, the image is upside down. Well, is this image a real image or a virtual image? An image formed by the actual intersection of refracted rays is a real image. So the image is real, it is smaller than the object, and it is upside down. Alright. Now let's place the object now at 2f. When the object is placed at 2f means at a distance twice the focal length of the lens. Where is the image formed? Let's construct that picture. This is my lens. Draw the principal axis. That's our principal axis. Alright. This is the principal focus on the left side. And this is 2 times f. 2 times the focal length. And this is the principal focus on the right side. And 2f on the right side. Where am I going to place the object this time? The object is going to be placed at 2f. So I'm going to have the object placed at 2f. Okay, let's take a ray that is parallel to the principal axis. A ray that is parallel to the principal axis, after passing through the lens, where will it go? It will pass through the principal focus. There we are. Alright. Another ray we can take is the ray that passes through the center of the lens. If a ray passes through the center of the lens, it will go without any deviation. There we are. This ray goes without any deviation. Now, where is the image formed? Image is formed at a point where the refracted rays actually meet. Now, you must understand that we are only constructing the image of the top of the object. So, the top of the object now looks, it is here. So, this position is the image of the top of the object. So, this is the image of the object. Where is it formed? It is formed at 2f on the other side of the lens. Now, what can you say about the relative size of the, look at the size of the object. Now, bring it over here. It is exactly the same as the size of the image. The size of the object and the size of the image are exactly the same. The object is erect, the image is upside down. So what are the characteristics of the image one more time? When the object is placed at 2f on one side of the lens, the image is formed at 2f on the other side of the lens. The image is of the same size as that of the object. It is formed at 2f and it is inverted. Is this image real or virtual? Because the image is formed by the actual intersection of the refracted rays, this image is real. Alright. Let's now place the objects between f and 2f. Can you give it a try on your own? Something that we just saw. Draw a diagram on your own. Place the object between f and 2f of the lens. Alright, let's draw that diagram. That is my lens. Draw the principal axis. There is the principal axis. Mark f, 2f on either side of the lens. You got f there, 2f there, f on the right side, 2f on the right side. Where is the object going to be placed? It is going to be placed between f and 2f. There we are. That's the object placed. Okay, let's choose two light rays. Which are the rays we're going to choose? A ray parallel to the principal axis. After refraction, will pass through the principal focus. There you are. And a ray that passes through the center of the lens will go undeviated. Now look where they are meeting. Where is the image formed? The image is formed way off 2f. It is beyond 2f on the other side of the lens. So if that is the object, then this is the image. Tell me some of the characteristics of this image. You can see the image is much bigger than the object. It is obviously upside down. Is it real or virtual? It is real because it is formed by the actual intersection of the light rays. Okay, I hope you understand how we construct images. I will show you some of these images a little later. Okay, the image is inverted, magnified. Magnified means bigger than the object, and it is formed beyond 2f on the other side of the lens. Now, this is how a projector works. Is that right? A projector, when you put a film slide between f and 2f of the lens, the image is formed beyond 2f on the screen, which will be much bigger and inverted. So in order to see the image erect, you must keep the object upside down. Okay, let's now see what happens when the object is placed between the principal focus and the lens. Bring the object closer and closer to the lens and keep it between the principal focus and the lens. Alright, let's draw this diagram. This is the lens, and what is this line that I drew? That is the principal axis. And the principal focus, 2 times f, that is on the left side of the lens. Let's mark these points on the right side also. There you are. Where am I going to place the object? The object is going to be placed between f and the lens. So the object is going to be placed very close to the lens. What happens? Alright, let's take a ray that is parallel to the principal axis. After refraction, it will pass through the principal focus. There it goes. Now let's take a ray that will be going through the center of the lens. It will go without deviation. And if you look, can these two rays meet to produce a real image? Well, no. These two rays cannot meet. But if you keep your eye here, and look from here, these light rays will appear to be coming from somewhere here. You see, this refracted ray will appear to be coming from there, and this will be appearing to come from there, and they too meet here, and that is where the image is formed. Now look at the way I used broken lines to represent the image. Why? This image is virtual. Why? Because it is not formed by the actual intersection of the light rays. It is formed by the illusion of the rectilinear propagation of light. So we have a magnified image. The image is erect this time. It is not inverted. It is not real. It is virtual. It is formed on the same side as the lens. That means this is the principle of what is called a magnifier. A magnifier. Now, let me see if I can show you some of these things quickly. Now I have a lighted object here, which is a bulb. Now over here, I'm going to keep it slightly below the camera, and I have a lens in my hand. Can you see this lens? Now I'm going to keep the lens in front of the object, and can you see the image? What you see on the screen is now the image of this lighted bulb. It's the filament of the bulb that is projected onto the screen. And if I move the lens, the image becomes blurred. Now move the lens towards the object, you can see the image is now clear. Okay, now I can also catch the screen. If I keep a screen there, I can catch this image on the screen. Now watch this. Now look at the image that I have caught on the screen. That's the image I have caught that on this white screen. And the image depends on the position of the object. If I move the lens away from the object, you can see the image becomes smaller. I need to move that screen far away. You see, I'm going to move the lens away from the object. The image becomes smaller. See that? Okay, now watch this when I keep the lens, or when the object is placed between the focal length and the lens. Now the lens is between the principal focus. Now you look through the lens and see how the light now look. It looks magnified, is that right? It looks very big now. Now this is how a magnifier works. Okay, let's move on. Now what kind of image is formed by a diverging lens? Now, irrespective of the position of the object, a diverging lens always forms a diminished, virtual, erect image. Now, this is the kind of image that is formed by a diverging lens. A diverging lens always forms, if this is the object, you can see a diverging lens cannot form a real image, because the refracted rays that gets diverged can never meet at a point. A real image can be formed only if the refracted rays meet at a point. For a diverging lens, that can never happen. So the image formed will be virtual, it will be small and formed on the same side of the lens. There you are, that's the object and that's the image. The image will be virtual, it is smaller than the object and formed on the same side of the lens. Alright, we are now going to do a lab on measuring focal length. Measuring focal length. Now, what is it that we need to measure in order to measure the focal length? Listen carefully for the method of the experiment. We will place an object at a distance u from the lens and obtain its image on a screen placed at a distance v from the lens. So, there are two distances we are going to be measuring. Now, what's this diagram? I have a ray box, which is going to be our object, and the lens, and we have a screen where the image is going to be formed. Let me show you, if I can, of the arrangement. I have mounted that on a system so that I can take the measurement. Now, this is the ray box. I can turn it on. Now, if I plug it on, I can turn the ray box on. Give me a second, I can do that. Over here, you can see this is the ray box and the lighted, this is the object. Okay, and now you have the lens. Can you see where the lens is? Well, that's the lens. and the image will be formed on a screen. This is the screen. Now, we said the distance of the object, this is the object, the distance of the object from the lens, we are going to call it u. Alright? So, u is the distance of the object from the lens. We will form the image of this object on the screen, and the distance from the screen to the lens will be called v. Those are the two distances we are going to measure. Okay. Now, focal length of the lens can then be calculated using those two distances. One more time, what are the distances? The distance of the object from the lens we are going to call u. And we will measure the distances in centimeters. The distance of the image, that is the screen, from the lens will be called v. And once you have u and v, we will use a formula to calculate the focal length. Look at the formula. F, the focal length, equal to u multiplied by v on the numerator divided by u plus v on the denominator. And use this formula and calculate the focal length of the lens. You ready? Let's go and do the experiment. So use the experimental values to complete the table on the next slide. Now here is the table. We will do trial 1, 2, 3, 4, 5. We will measure each u values, measure the corresponding v values, then you have to calculate the focal length and complete the worksheet and email that to me. Okay, let's set up the experiment. Alright, watch this setup. I have the object. Well, watch my hand. You can see my hand is in front of the object. That is the illuminated object, and I have the lens. And what do you call the distance between the object and the lens? The distance between the object and the lens is called u. And then the distance, I will move the screen. I will move the screen to get a very clear image. Look at that. I can move the screen back and forth to make the image very clear. Alright, my first u value is 12 centimeter. You can see I have darkened the room. You cannot see the screen, so you've got to write that down on your own. So trial number 1, the u value is 12 centimeter. Well, I'm going to write it on here, but you cannot see it because I have taken the light out of the room. Trial number 1, the u value is 12 centimeter. And I'm going to move the screen back so that I get a clear image. Now, you watch the image and see if I'm doing it right. I want to make it as clear as possible. Alright? My eye may not be a good one, but I'm going to keep this here. And the distance I am having here is... I need my glasses to read in the dark. Alright, that will be 29, 99, 20. That is 70 centimeters, 70. Now, what is this distance called? The distance from the lens to the screen now is called V. What is the V distance now? V is 70 centimeters. So write your distance V is 70 centimeters. Okay. Now we got one set of values. Now what I'm going to do is increase the distance U by 2 centimeters by moving the lens a distance of 2 centimeters. Now my U is 14 centimeters. You can see I don't see any image there. I now need to move the screen to get my clear image. Well, move the screen until you get a very clear image. Alright. Okay, so my U is 14 centimeter. My trial 2. U is 14 centimeter. What is my V? V will be 58 minus 96. That is 41 centimeter. 41 centimeter. So the distance V, when we changed U to 14 centimeter, V became 41 centimeter. Alright, in our next trial, I hope you're writing these values down. In my next trial, I'm going to make the distance 16 centimeter. Alright, I need to move the screen forward to get the clear image. Can you see the image becoming clear? Alright, that is now 65. That is 29 centimeter. The V value now is 29 centimeter. U is 16. So, for our third trial, are you following? For the third trial, the value of U is 16 centimeter. The value of V is 29 centimeter. I'm now going to change the value of U to 18. Alright. I need to now move the screen to get my image clear. There it is. Alright, that will be that will be 24. My V now is 24. When U value is 18, my V value is 24 centimeter. Okay, one more reading. We're going to make the U value to 20 centimeter. Is that right? And now you got to move the screen to get a very clear image. And that seems to be 19. Well, that's trial number 5. Your U value is 20 centimeter and your V value is 21 centimeter. 21 centimeter. Okay, we have finished with the trials. I'm going to turn the light back on, and there you can see all the values that I have obtained. You have the U and V values. Alright. What are you supposed to be doing? Calculate the focal length of the lens. What is the formula for the focal length? Focal length is, you got U values and V values. Focal length is U multiplied by V divided by U plus V. So complete this table, calculate the 5 values of the focal length and find an average value. Alright? Okay, let's go on. So calculate the focal length for each trial and obtain its average value. Complete the worksheet for this lab and email it to me. Now, although I'm doing the lab work, I would like you to be involved in it so that you get the feel, the experience of doing the lab. Alright?